So in this video, let's look at t-test now, and let's also consider that we had our initial Z distribution for our data set, and we're comparing a particular data point X compared to the population mean for that entire population comprising that data set, and a standard deviation to look at how that data point fits into the wider distribution. And we have a comparison that if we have a large number of samples, we can test that sample mean X against the population mean mu, adjusted for the standard deviation over the square root of n, where this comprises the standard error. However, if you have fewer samples, roughly speaking less than 30, we're better off using a t-distribution that approximates the normal distribution with the same metrics, where we're dealing with a kind of pooled standard deviation here. So that's a one sample t-test. So we have one reference point to compare to the mean and our standard error as a denominator. If we're comparing two different samples, we might have two different groups that have some sort of effect size difference between the different groups. We can use the t-test, and with RStudio, that's going to be with Welch's t-test. So that means we're comparing the difference in the means by the pooled standard error as the denominator for sample size n and m, where on paper we might take the shortcut of calculating the degrees of freedom to be n plus m minus 2, which corresponds to students' t-test degrees of freedom. With Welch's t-test degrees of freedom, we got a more accurate estimate. And you know that the sample sizes are denominator here. So the standard deviations will have an effect in relation to the sample sizes on how much variation there is within the samples, which means that for some samples, we might find the degrees of freedom are much smaller than the criteria given by students' t-test. So Welch's t-test will give us a quite slightly different result that's more accurate. We're making a number of assumptions here, as mentioned before, that the variances are comparable, and the t-test is robust to these similar variances, that the sample sizes of n and m are around the same, and that the two groups being compared are not correlated. If they're correlated, obviously, then that will affect our experiments. So let's look at this in RStudio. Okay, so what we have here is that we're using the OR-norm function to generate 100 values with a mean of 10 and a standard deviation of 12. So each time we run this function on line 60, we'll see that the numbers differ. In the same way, we can use OR-norm to generate 10 numbers with a mean of 22 and a standard deviation of 8. If we run that function a few times, you'll see, again, the numbers are different every time. If you do want to round the numbers, you can just wrap the round function around this. So that is round brackets. And we can give as a second argument after the OR-norm function, the number of digits to which we'd like to round. So you can see there we're rounding to 2 digits, and then we can round to 1 digit as well if you want to, if you're just curious about that. So what we can do is generate data for our C57BL mice, and we're going to compare them to these falconer mice. And these are the mice weights, for example. I hope it's a decent approximation of that. And we're going to compare the mice weights using these numbers. So what we might do first is plot these. So we can plot them individually, or it's a 1-by-1 plot here, like on the right for a histogram, or we can plot them side by side. So if you just plot them individually, we can take the C57BL data, which we have there, and we can do a histogram like that and see their distributions, and add a grid if we want as well. We might widen this a bit to see them more clearly, and we might add more breaks to make it more resolved a little bit. Let's say 12. There you can see, and then we can do the same for the falconer ones. So we can see those as well, and then we can do it a 2-by-2 plot, top and bottom, I think, and use those functions we did there. So you have CBL on top, and then the falconer at the bottom. So you can sort of see how they're different or not different. So what we want to add to this is then going to be, so to rescale the axis for each of these, we can just add on a YLEM parameter. So we go, sorry, x lim parameter. So x equals c concatenating together, let's say 25 and 55. And what we can note then is that's the same if for each of these. We can just copy our code over. So the first one, and then we put in Falconer there, and we can see that we have more comparable set of distributions to compare them against each other. So you can see that there's definitely a difference that Falconer are heavier and the others are lighter. We can use this code here to plot the sorted values for C57BL in blue with the grid, which you see in top. And we can do the same for Falconer using the points command to plot them in red and mapping this on top. So we're going to have a single plot here for these two. And we can map their Falconer on top. You can see an average that there is a difference there. However, the question is whether the patterns across the whole underlying population of Falconer show a difference compared to C57BL. So we can also use the box plot function to plot them too in that way, and you can see the same difference. So there's different ways of visualizing this data. So that has the names parameter here that adds in the names. If we see the bottom of this graph, and I've removed the gray barrier here just to show the names. And then we use the TSS function to compare these. So each of these is just a simple vector of the data associated with each of these groups. And we put in each of these values in there. So we're comparing X versus Y. And we're using the t-test function. So if we run the t-test function altogether on line 78, what we see is that it has, we're running a Welch two-sample t-test. And then we're comparing C57BL and Falconer. You can see the t value is negative, suggesting that the C57BL ones are less than the Falconer ones on average. And we see that in the average estimates for them at the bottom. That's 36.1 for the C57BL and 41.6 for Falconer. The degrees of freedom is 49.2, whereas we would expect if we had the students approach that we have the length, the number of samples in each of these, -2 would our number of degrees of freedom, so that will be 58. And we see the p-value there is quite small, suggesting this is quite extreme. So that suggests that there is some difference between Falconer and C57BL, and we can explore that further by looking at the confidence interval to see that on average, the C57BL, the population estimate of the mean difference, if we repeated this experiment, will be that the C57BL is 8.7 to 2.3 grams lighter than the Falconer ones at 95% of the time. That will be our sample mean difference. So if this confidence interval overlapped, so that the difference was say -8.7 and plus 0.2 overlap to 0, the plus 0.2, that would mean that this is not a reliable result, that there may be certain situations where we sample each of these mice groups and we find no difference, in which case we find that the p-value is much higher, maybe have at the 6th percentile. So we can extract the statistic value using the dollar sign. So if we take this whole vector, we can extract certain information in there, and we can do that by assigning that to a new vector. We can see what's inside there. So YY is this new vector. And if we look at the structure of YY, we can see what's inside there. So you can see there we have the statistic, which is the t value there. So go YY dollar statistic. You can see that there, YY dollar, the parameter. There's the degrees of freedom, YY dollar, the p-value. We can extract that p-value directly, YY dollar, confidence interval. We got two values there. And then the YY dollar, the estimate is the estimates for each of these. And then YY dollar, what's the next one? The null value, that's the null hypothesis, that the difference in the means is 0. And then we have our alternative hypothesis, is that it's two-sided. So we're comparing the groups that the one might be bigger or smaller than the other. YY dollar, the standard error, is 1.6, which kind of matches what we expect with this data. And then we have the method, which is, well, two sample t-test. And then we have the data name, which is the group name. So all that is in there. We can also extract that information using the square brackets too, if you wanted to, in the same order, but that's not necessarily as intuitive. It depends what you wish. So you can try this by making your own distribution of mouse weights and getting the t-test and statistic p-values and so on using t.test. If you want to look at students' t-test, the key feature is that we have var equals false. So this above one is two sample t-tests with students' t-test, where we're assuming that the variances are equal. If we look at that, so let's look at the standard deviation of C57BL and standard deviation of the Falconer. We see that the variances are actually not equal. They're somewhat different. So when we compare that to Welch's t-test, we see that we get that degrees of freedom 49.2 and p-value 0.001175. Whereas if we toggle this, so we're changing this to t for true, we see that the p-value is different. It's actually smaller here, and we get degrees of freedom that's 58. So this is a less accurate estimate for the student's t-test, because the degrees of freedom estimation is smaller, even though the confidence interval and the mean values and so on are actually the same. So we can also compare these as if they're paired before and after. If we look at the data, you can see that they're at least have the same number of entries, allowing this to be possible. So this one we would see a change of 12, and this one would be a change of 11. This one would be a change of minus 11. This one would be a change of +4, and so on. So we look at the differences if we have the paired parameter set to true. So if we try that one, what we are doing is a paired t-test. We see the t-value is actually comparable as if we did a two sample t-test. Degrees of freedom is different because we got one group, and here the p-value is 0.00132. So it's just there is a big difference before and after if this was a paired situation. So that kind of concludes this portion of this section on using RStudio to do t-tests.